Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through fascinating space facts about the violent events that helped build worlds like Earth. The story begins with a strange contradiction. Earth feels calm beneath us. It holds oceans, air, forests, cities, weather, and life. Yet the planet was not born calmly. Earth was shaped by supernova shockwaves, colliding dust, molten rock, wandering protoplanets, a Mars-sized impact, icy comets, and asteroid storms. For now, imagine leaving Earth slowly, rising above the clouds until the planet becomes a blue curve against black space. From that height, Earth looks complete. The oceans seem permanent. The moon seems placed exactly where it belongs. The thin atmosphere glows like a border of light. But none of those things were guaranteed. If the early collisions had been slightly different, Earth might have shattered. If the young planet had lost its iron core, it might have had no magnetic shield. If water had never arrived from colder regions of the solar system, the surface below you might have stayed dry and silent. If the moon had not formed, the tilt of Earth could have wandered wildly, making stable seasons harder for life. So tonight's journey is not simply about disasters in space. It is about how disaster can become construction. A supernova can destroy a star and help make a new solar system. A collision can melt a planet and also give it a moon. An asteroid can carve a crater and also carry water-rich minerals. A comet can threaten life and also bring ingredients from the deep cold. The universe is not gentle in the ordinary sense, but it is creative. It builds with heat, gravity, impact, chemistry, and time. Long before Earth existed, the material that would become Earth floated inside a vast cloud of gas and dust. Clouds like this still exist in the Milky Way. One of the most famous examples is the Eagle Nebula, where the pillars of creation rise like dark towers against glowing starlight. Those pillars look solid in photographs, but they are not solid like stone. They are enormous clouds spread over trillions of miles. If you could drift inside one, the gas would be thin, cold, and almost empty by earthly standards. A mountain-sized volume of that cloud might contain only enough material to make a small rock. That is one of the first useful pictures for tonight. Space can look dense and dramatic from a distance, but up close it can be impossibly thin. To turn such a thin cloud into stars and planets, something has to squeeze it. A possible trigger is a supernova, the death of a giant star. A massive star reaches the end of its life, collapses, and blasts material outward so violently that for a short time it can outshine an entire galaxy. The shockwave moves through space like a wall of energy. When that wall reaches a quiet molecular cloud, it can compress the gas and dust into dense knots. Imagine standing far away from the pillars of creation and watching a shockwave approach. Nothing would look fast at human scale because the distances are too large. But the wave is racing through space at millions of miles per hour. It is the aftershock of a star's death, and when it reaches the cloud begins to change. Parts of the cloud collapse. Gravity takes over in the densest regions. A new star begins to grow at the center of a spinning disk. Around that young star, leftover dust and gas flatten into a broad whirlpool. In one such disk, more than 4.5 billion years ago, the Sun was forming. Around the Sun, the first material that would become Mercury, Venus, Earth, Mars, asteroids, and comets was beginning to organize. This is the first connection. Earth did not begin with Earth. Earth began with older stars. The atoms in the ground, the iron in the core, the oxygen in water, and the carbon in living things were all part of a longer cosmic chain before they became part of home. The analogy is not a peaceful workshop. It is more like an old building collapsing and the debris becoming a new city. One star dies. The shock wave from that death helps gather the raw material for another star. Around that new star, planets begin. If you were approaching the newborn solar system from outside, you would not see a finished family of planets. You would see the young sun glowing inside a dusty disk. The disk would be wide, hot near the center, colder farther out, and full of tiny grains moving in orbit. Somewhere inside that disk, Earth would be nothing more than scattered dust. The journey from dust to planet is the next mystery. At first, the material that would become Earth was too small for gravity to matter. Gravity shapes galaxies and pulls planets into orbit, but tiny dust grains do not have enough mass to pull strongly on one another. If gravity cannot bind the first grains, something else has to begin the work. One useful earthly analogy is static electricity. Dust grains in a young solar disk can cling in a way that feels almost like clothes sticking together after coming out of a dryer. The charges are tiny, but at that scale they matter. A dust grain touches another dust grain. The grains cling. Then more grains cling to the little cluster. Imagine being small enough to float among those grains. You are inside a disk around the young sun. The sun is not yet the calm yellow star we know from Earth. Around it, dust and gas sweep in great orbital paths. The grains are not trying to become planets. They are simply bumping, clinging, separating, and clinging again. The first planet building is not majestic. It is almost absurdly delicate. Worlds begin as dust bunnies. That image matters because it slows the mind down. Earth did not appear as a globe. Earth passed through stages that would not look like Earth at all. Dust, fluff, pebbles, tiny melted droplets, rock, rubble piles, asteroids, and then larger planetary embryos. The ground under your feet has an ancestry that begins smaller than a pinhead. Another process may have been lightning-like heating inside dusty clouds. In the early solar system, some dust balls were heated suddenly and intensely. Tiny melted droplets cooled into solid beads. Meteorites still preserve little round grains like these, ancient objects that formed before the planets were complete. So the first true facts in the journey are not only large facts, they are small facts. Static charge can help dust stick. Heat can fuse grains into tougher pieces. Collisions can gather fragments. Over time, the disk changes from smoke-like material into pebbles and rocks. Here, the pace stays slow because each force arrives in its own time. Static electricity begins the tiny work. Heat and collisions strengthen the material. Gravity arrives later when the pieces become large enough. If you were traveling through the disk at that stage, Earth would still be impossible to point to. There would be no blue world, no moon, no oceans, no continents. There would be a swarm of particles orbiting the young sun, each particle part of a long experiment in sticking together. The analogy is a construction site before the buildings have foundations. The material is present, but the structure is not. Dust becomes clumps. Clumps become pebbles. Pebbles become rocks. Rocks become asteroids. And asteroids become the first rough bodies large enough for gravity to take seriously. That transition from weak sticking to gravity is one of the most important steps in the whole story. Gravity enters the story when the growing bodies become large enough. A tiny dust grain cannot pull another dust grain very hard. A mountain-sized body can. Once a rocky object reaches that scale, it begins to attract nearby fragments, and growth speeds up. Imagine Pikes Peak removed from Earth and placed alone in the young solar system. If you were floating nearby, you would not feel a sudden violent pull like falling from a cliff. You would begin to drift. Slowly at first, then faster. The mountain's gravity would gather you in. That is the moment the story changes. Before gravity, growth depends on chance encounters. After gravity, the larger bodies have reach. They can pull in neighboring rocks that would otherwise pass by. The more material a body gathers, the stronger its gravity becomes. The stronger its gravity becomes, the more material it gathers. This feedback loop turns slow growth into faster growth. The young solar system becomes filled with protoplanets, baby worlds moving around the sun. These bodies are not smooth planets yet. Many are lumpy, battered, and irregular. Some look less like worlds and more like smashed potatoes or distorted peanuts. But size changes shape. When enough rock gathers in one place, self-gravity begins to crush the body inward. Tall mountains cannot stand forever on a large enough world. Rock can slowly deform under enormous pressure. The most efficient shape is round, so a growing protoplanet begins to become a sphere. This is a quiet but beautiful idea. Roundness is not decoration. Roundness is gravity sculpting matter into balance. If you were approaching young Earth at that stage, it might not look like a place to land. It would be smaller than Earth today, hot, cratered, and unstable. Rocks would still be falling from space. The surface would be wounded again and again by impact energy. Each impact would add heat. Each impact would add material. Each impact would help erase the previous surface. Think of the young Earth almost like a blast furnace. The young planet became molten. Heavy iron sank. Lighter rock rose. A body that had been a mixed pile of material began to separate into layers. This is not just a geology detail. It is part of why Earth could become habitable. As molten iron sank toward the center, Earth began building an iron core. Over time, motion in that core helped generate a magnetic field. That magnetic field became a shield, protecting the atmosphere and surface from charged particles streaming from the sun. So the molten Earth is not only a frightening scene, it is a necessary scene. The heat that made early Earth hostile also helped organize the planet inside. The core, the crust, and the magnetic shield all belong to the same chain. Imagine standing impossibly above that young planet. Below you is no ocean and no green land. There is a red-orange surface, lava, falling rock, and a sky filled with debris. In the distance, volcanoes thunder. The entire world glows with stored impact energy. It is not yet home. But the structure of home is forming. The early solar system was not a set of finished planets moving calmly in their lanes. It was crowded with protoplanets. Many of them crossed paths. Some merged, some shattered, some were swallowed by larger bodies. This violent era is one of the reasons Earth exists at all. One impact rises above all the others. The collision with Theia, a Mars-sized body that struck the young Earth. If Theia had hit straight on, Earth might have been destroyed. Instead, the impact was likely a glancing blow. Still, it was one of the most violent events in Earth's history. Imagine approaching Earth just before that collision. The planet is already round. It has an iron core and a rocky exterior. It is still young, still hot, still surrounded by debris. Then another world appears, not a stone or a small asteroid, but a body roughly the size of Mars. At orbital speed, a world that large is not simply a projectile. It is a planet-scale event. When Theia strikes, Earth melts again. The impact blasts material into orbit. Rock vapor, molten debris, and torn planetary material spread around Earth as a glowing ring. From that ring, smaller bodies gather. It is possible that two moons formed first and later merged into the single moon we see today. That detail gives the journey a strong visual sequence. Impact, ring, two moons, one moon. It should unfold slowly. For a long time after the impact, Earth's sky would have looked nothing like the sky tonight. The moon, or moon-like bodies, would have been much closer. Tides would have been stronger. The young surface would still be cooling from catastrophe. But this disaster gave Earth one of its most important companions. The moon is unusually large compared with Earth. Because of that, Earth and moon almost feel like a double system. The moon helps stabilize Earth's axial tilt. That stability helps keep seasons more regular over long spans of time. This is where the connection to life should be gentle and clear. The moon did not create life by itself, but a stable tilt can help create stable climate patterns. Stable climate gives chemistry and biology time. Life does not need a perfect world every day, but it does need enough continuity to persist and evolve. The analogy is a spinning top. Without a steadying influence, a planet's tilt can wobble more dramatically. With the moon nearby, Earth keeps a steadier posture as it travels around the sun. If you were watching Earth from space now, the moon would seem calm and familiar. But in this story, the moon is the cooled remnant of a collision that almost ended Earth before Earth had truly begun. The same event that could have scattered our planet into debris helped create the companion that steadied it. This is not a rapid fact. It is a transformation. A catastrophe becomes part of habitability. A collision becomes a clock in the sky. A disaster becomes part of the reason Earth can feel dependable. After the moon-forming impact, Earth was still not the blue planet. The young Earth was hot and dry compared with the world we know now. Water had to arrive, survive, or both. To make oceans, Earth may have needed material from far colder regions of the solar system. Near the young sun, heat made it harder for ice to survive. Farther out, beyond the warmer inner region, water ice could gather in comets and water-rich asteroids. Those bodies formed in the cold, but gravity did not leave them quietly in place forever. Jupiter, Saturn, Uranus, and Neptune shifted during the solar system's early history. Their gravitational relationships disturbed huge populations of asteroids and comets. Picture a bowling ball rolling through pins, except the pins are icy bodies, rocky fragments, and ancient leftovers moving through space. Picture the outer solar system as a cold storage region filled with icy bodies. Then the giant planets begin to rearrange. Jupiter and Saturn tug in repeating patterns. Neptune and Uranus shift. Orbits that had been stable become unstable. Icy bodies are scattered inward and outward. Some are thrown toward Earth. From Earth's surface, that delivery would not look gentle. It would look like bombardment. Fireballs would cross the sky. Impacts would melt ice, blast rock, and change the atmosphere. But inside that violence was a delivery system. Comets are often described as dirty snowballs, but that phrase can make them sound too simple. A comet is a frozen archive. It can contain ice, dust, carbon compounds, and material preserved from the young solar system. Asteroids can also hold water-rich minerals. Every impact could deliver a small part of what later became oceans, clouds, rivers, glaciers, and perhaps the chemistry that life needed. When you drink a glass of water, some of that water may carry a history older than Earth as a finished world. The water in a glass, the water in rain, and the water in the ocean may have links to material that began beyond the warm inner solar system. If you were approaching Earth after this long bombardment, the planet would begin to look different. Steam would rise. Rain might fall for extraordinary lengths of time. Basins would fill. The surface would cool. A planet that had been molten and dry would begin to carry oceans. The important emotional shape is not simply that water arrived. It is that Earth became habitable through a chain of unlikely exchanges. The outer solar system gave the inner solar system ice. The giant planets disturbed the small bodies. The small bodies struck Earth. The impacts were destructive, but the material they carried became part of life. The best facts do not sit alone. They connect scales. A comet in deep cold, a planet's orbit, a glass of water, and the possibility of life. Asteroids built Earth, but asteroids also threaten Earth. That dual nature is one of their strangest qualities. The same class of objects can help make a planet, bring water, preserve early chemistry, carve craters, end whole chapters of life, and someday provide resources for future space settlements. The asteroid belt is the leftover construction zone between Mars and Jupiter. Popular images make it look crowded, but real asteroids are separated by enormous distances. If you flew through the belt, you would not dodge rocks every second. Most of the time, space would still look empty. The danger is not crowding. The danger is speed, mass, and rare intersections. Jupiter explains part of the belt's history. Its gravity stirred material that might otherwise have continued growing into a rocky planet. Instead of one world, the region became a belt of fragments. Rocky bodies, metallic bodies, icy bodies, rubble piles, and small worlds like Vesta and Ceres. Vesta is especially fascinating because it is not just a rock. It has a differentiated interior, meaning it once became hot enough for material to separate. It has scars, a surface, and a history. Vesta is like a preserved piece of the planet-building process, a way to glimpse what an early rocky world might have looked like before it became Earth-sized. Ceres gives a different kind of wonder. Ceres is darker and colder, with evidence tied to water-rich material. Objects like Ceres may help explain where some of Earth's water came from. Whether or not every detail is settled, the asteroid belt is not dead rubble. It is a library of early solar system material. Now drift toward the moon. The moon's craters preserve the history that Earth has mostly erased. Earth has weather, oceans, volcanism, and plate tectonics. The moon has no rain to smooth its scars and no active surface recycling like Earth. When you look at the moon, you are looking at a record of impacts. For every large crater on the moon, Earth would have taken many more hits because Earth is a larger target. Earth does not look as scarred because Earth heals, erases, and recycles. The moon remembers. Then the story turns toward the impact that helped end the age of dinosaurs. The boundary layer left behind is rich in iridium, an element rare on Earth's surface but more common in asteroids. A thin layer of rock becomes evidence of a sky event. Dust from an asteroid impact settled around the world, marking a before and after in the history of life. But even here, the point is not fear. The point is that asteroids are two-sided. They help build worlds and they can reset worlds. They are creation and destruction wrapped together. If you were standing in a dark field tonight and saw a shooting star, you would be seeing a tiny piece of space burning in the atmosphere. Most are harmless grains. Some are large enough to reach the ground. A few, over deep time, are large enough to change biology. That contrast gives the journey its shape. Dust streak, meteorite, crater, extinction, telescope, defense. The same sky that gave Earth material also requires watching. Once the story reaches dangerous asteroids, there is an important modern turn. The dinosaurs could not watch the sky with telescopes. We can. That difference changes the meaning of an asteroid threat. Most near-Earth objects are small. Many burn harmlessly in the atmosphere as meteors, but larger objects need attention because they carry enormous energy. A rock only tens of yards across can carve a crater. A body miles wide can disturb the climate of the whole planet. The danger is not only size, but speed. A small mountain moving through space is not like a mountain sitting still on Earth. Its motion is stored energy. Imagine an asteroid crossing Earth's orbit. From a great distance, it might look quiet, just a dark point moving against darker space. But if its path intersects Earth at the wrong moment, that quiet object becomes a planetary event. The atmosphere glows, the ground shakes. The impact releases energy in seconds that had been carried silently for millions of years. This is where radar and telescopes enter the journey. A telescope can find a moving dot. Radar can send a signal toward an asteroid and receive the echo. From that echo, astronomers can refine the asteroid's distance, speed, shape, and future path. The sky becomes not only a place of wonder, but a place we can measure. Apophis is a useful example. It is an asteroid that once made astronomers uneasy because early calculations left a small chance of a future impact. More observations refined the orbit and removed the immediate danger. Science did what we needed to do. It narrowed uncertainty. Fear becomes measurement. Measurement becomes a clearer path. If a dangerous asteroid were found early enough, the goal would not necessarily be to explode it. Breaking a large asteroid into several pieces could make the danger worse. A gentler idea is to change its path slightly while it is still far away. Over millions of miles, a small change can become a miss instead of a hit. The analogy is steering a ship long before it reaches the harbor. Close to the rocks, a tiny turn is not enough. Far away, a tiny turn can matter. In space, time is part of the defense system. Asteroids are not only threats. Some contain metals, some contain water. In a future where humans build farther from Earth, asteroids may become construction sites, fuel depots, radiation shielding, or stepping stones. A body that would be expensive to launch from Earth is already in space. That thought should stay quiet and speculative, not overpromised. We are not saying asteroid cities are near. We are saying the same objects that helped build Earth may someday help humans move beyond Earth. The relationship changes. First, asteroids were ingredients. Then they were hazards. Later, they may become tools. A strong space fact can have a past, present, and future. Asteroids made Earth. Asteroids threaten Earth. Asteroids may help us leave Earth. One object class can carry a whole arc if we give it enough room. The next thread is orbit. Gravity, speed, distance, and time all belong here naturally. Earth's orbit is nearly circular. That matters. Because Earth stays at roughly the right distance from the Sun, temperatures remain within a range where liquid water can persist across long spans. If Earth moved significantly inward, it would become more Venus-like. If Earth moved significantly outward, it could freeze more deeply. Habitability depends not only on what a planet is made of, but how it moves. An orbit is a balance between falling and sideways motion. The Sun's gravity pulls Earth inward. Earth's sideways speed keeps it from falling directly into the Sun. The result is a long, curved path around the star. The same idea shapes moons, asteroids, comets, planets, binary stars, and galaxies. A simple analogy is throwing a ball. Toss it gently, and it falls back. Throw it faster, and it travels farther before falling. Imagine throwing it so fast and from so high that as it falls, Earth's surface curves away beneath it. That is orbit, falling around a world instead of falling straight down. Peaceful orbits can become extreme. Mercury travels close to the Sun, where heat is intense and its orbit is stretched. Pluto moves far away, taking centuries to complete one circuit. Comets can fall from the outer solar system toward the Sun on long, narrow paths. Near the Sun, they accelerate dramatically, their frozen surfaces waking into jets, tails, and glowing comas. If you were riding beside a comet from the outer solar system inward, the trip would feel like falling down a gravitational hill. Far from the Sun, the comet is cold and almost inert. As it approaches, sunlight warms the ice, gas escapes, dust lifts away. A tail forms, not simply behind the comet's motion, but pushed by sunlight and the solar wind. That detail matters because it turns a familiar picture into physical understanding. A comet's tail is not smoke trailing from a moving object. It is material being driven away from the Sun. Orbits also become stranger beyond our solar system. Hot Jupiters orbit extremely close to their stars. Some planets move on stretched paths. Some planets may be thrown out entirely and become rogue planets, wandering between stars without a parent sun. Gravity does not only bind systems together. Under the right circumstances, gravity can eject worlds into darkness. Gravity does not need to be named in every sentence to be felt. It pulls, steadies, disrupts, ejects, stretches, and returns. You learn the force by watching what it does. After leaving Earth's calm orbit, it becomes easier to realize how unusual calm can be. Earth is not safe because the universe is gentle. Earth is safe because many things happen to settle into a long-lasting balance. Earth's orbit feels normal only because we live inside it. The wider universe shows that orbits can become far stranger than the paths of the familiar planets. Some planets orbit their stars in only a few days or even less. These hot Jupiters are giant worlds pulled close to their suns, far closer than Jupiter is to ours. They may have formed farther out and migrated inward, pushed and pulled by gravity until they settled into a blistering orbit. A planet like that can be heated to thousands of degrees. Winds can race across its atmosphere. The star can tug the planet into a stretched shape. If you were approaching one of those worlds, it would not feel like visiting a larger version of Jupiter. The star would dominate the sky. The planet would move so quickly that the year might be shorter than an Earth day. Heat would pour across the upper atmosphere. The orbit itself would feel like a trap, stable for now, but not necessarily forever. Some planets become rogue planets, worlds that do not orbit any star. That idea is powerful because it breaks the ordinary definition in the mind. A planet is supposed to belong to a star. yet gravity can throw planets away. In a young system, large worlds tug on one another, exchange energy, and sometimes eject a planet into interstellar space. Imagine a planet drifting alone between stars. There is no sunrise, no parent star fills the sky. The world moves through the galaxy in cold darkness, warmed only by internal heat or wrapped in whatever atmosphere it managed to keep. It may once have belonged to a solar system. Now it is an orphan of gravity. Binary stars and compact objects push the idea even farther. Two white dwarfs can orbit so close that a whole orbit takes only minutes. A teaspoon of white dwarf material can weigh tons. When objects like that orbit each other, gravity is not a gentle background force. It strips material, heats gas, and can lead towards supernova explosions. Here, extreme physics can stay visual rather than becoming a list of strange objects. Orbits are not just circles, orbits are relationships. A planet and a star, a moon and a planet, two dead stars, a star and a black hole, two galaxies moving toward each other. The orbit tells you how gravity and motion are negotiating. Near black holes, the negotiation becomes extreme. Gas can spiral inward and heat until it shines in X-rays. Stars can race around unseen mass. Light itself can bend. Time and space are no longer separate pieces of scenery. They become part of the event. Extremes work best as contrast, not as noise. Earth feels more precious after we visit unstable orbits, rogue planets, white dwarfs, and black holes. The calm orbit of our own planet becomes meaningful because the universe offers so many other possibilities. Feel this as travel. Start with Earth moving calmly around the sun. Move outward to comets falling inward. Move farther to planets too close to their stars. Then drift into starless space with rogue planets. Finally approach the compact, fast, heavy systems where gravity writes the story in a more violent hand. After that, returning to Earth should feel like returning to a rare kind of quiet. Comets give us one of the most immersive travel sequences in the solar system. They begin in deep cold, far from the sun, sometimes in regions like the Kuiper Belt or the distant Oort cloud. They can remain there for millions or billions of years. Then a small gravitational nudge changes everything. Imagine a comet in the dark outer solar system. It is a frozen body of ice, dust, rock, and organic material. It may be only a few miles across, yet it carries material almost as old as the solar system itself. For most of its life, it does very little. Then a passing star, a collision, or a planetary tug changes its orbit. Slowly at first, the comet begins to fall inward. As the comet approaches the sun, speed increases. The sun's gravity pulls harder. The surface warms. Frozen gases begin to vaporize. Jets burst from cracks. Dust lifts away. A coma forms around the nucleus, making the comet appear much larger than the solid body at its center. A comet's tail can stretch for tens of millions of miles. Some comets shed enormous amounts of ice and gas every second. Some become unstable and break apart. A tiny nucleus can create a glowing cloud larger than planets. A dark, frozen object can become one of the most beautiful sights in the sky. If you were approaching the comet, landing would be nothing like landing on a planet. Gravity is weak. There is no air for a parachute. The surface may be dark, brittle, dusty, uneven, and venting gas. A lander needs to touch gently and hold on, almost like anchoring to a drifting iceberg in space. That is why the Rosetta mission is so memorable. It is not only a mission name, It is a spacecraft chasing a small target moving around the sun, trying to land on a body with almost no gravity. The lander must hold itself down because the comet will not hold it strongly. Comets are also chemically important. Missions have found complex material in comet dust. Comets carry water, carbon compounds, minerals, and organic molecules. That does not prove that comets brought life to Earth, but it makes them serious players in the story of life's ingredients. The key is uncertainty with wonder. Comets may have delivered some of the raw material for life. The evidence is suggestive. The question is still alive. A comet can be a threat, a messenger, a chemical archive, and a possible delivery system for ingredients that later became part of living worlds. After Earth has been built in the story, a natural question appears. If this chain of events happened here, could it happen around other stars? The answer should be careful. Earth is not the only rocky planet in the universe. Planet formation appears to be common. Stars form inside clouds. Disks form around young stars. Dust gathers. Planets appear. We have found thousands of worlds around other suns, and the numbers suggest that planets are not rare accidents. But an Earth-like world is not just a rock at the right distance. Many conditions had to line up. Earth needed a stable orbit, a long-lived star, enough mass to hold an atmosphere, enough water, chemistry, a protective magnetic field, and long spans of time. Earth also has the moon, which helps stabilize its tilt. None of these ingredients alone guarantees life. Together, they create a planet where life can persist. Imagine traveling to another young star. From far away, the star might look ordinary. Around it, a disk of dust and gas may already be thinning. Inside that disk, rocky bodies collide. Farther out, icy material survives. Giant planets may be forming and shifting. Comets may be scattered. A rocky world may be growing in the warm zone where liquid water could someday exist. The scene feels familiar because it echoes our own beginning, but it will never be exactly the same. The disk may have more dust or less. The star may be quieter or more violent. The giant planets may stay far away or migrate inward. The rocky planet may keep its water or lose it. It may have a large moon or no moon. It may be struck too often or not enough to receive the material it needs. This is where odds become emotional. The universe contains hundreds of billions of galaxies, and our galaxy alone contains vast numbers of stars. With so many chances, it feels natural to imagine other Earths. But Earth is not simply one condition. Earth is a sequence. A habitable planet is not a single lucky roll. It is many rolls over time. The right cloud, the right star, the right distance, the right chemistry, the right impacts, the right orbit, the right atmosphere, the right quiet stretches between disasters. That thought should not make Earth feel lonely. It should make Earth feel specific. Somewhere else, around another star, a different chain may have produced another ocean world. Perhaps another sky has a moon. Perhaps another planet carries water delivered from cold outer regions. Perhaps another civilization looks up and wonders whether its own world is rare. We do not need to answer that question tonight. It is enough to feel the scale of it. Earth is one known example inside a universe large enough to keep the question open. By the end of this journey, Earth should feel less like an ordinary planet and more like a finished sentence written by many violent drafts. A supernova may have helped compress the cloud that formed the sun. Dust grains stuck by tiny electrical forces before gravity mattered. Gravity gathered rocks into asteroids and protoplanets. Impacts melted the young Earth, helping separate iron from rock and build the core. A Mars-sized collision nearly destroyed the planet, but helped create the Moon. Icy asteroids and comets may have delivered water and organic material. Later impacts scarred the Moon, shaped Earth, and changed the history of life. The idea is not that disaster is good. The idea is more subtle. On cosmic timescales, creation and destruction are often the same process viewed at different moments. An impact can erase one surface and expose another. A supernova can end one star and enrich the next generation. A comet can threaten a planet and also carry ancient ice. A moon-forming collision can melt Earth and then leave Earth with a stabilizing companion. If you imagine traveling back toward Earth now, after all of that history, the planet looks different. The blue color is not simple. The oceans may carry material from distant cold regions. The Moon is not just a lamp in the night sky. It is a remnant of impact and a partner in Earth's stability. The magnetic field is not invisible trivia. It is tied to the molten iron core that formed when the planet separated inside. The ground beneath us becomes stranger. The water in a glass becomes older. A shooting star becomes part of a bigger family of events. Even the quiet Moon becomes a record of violence that Earth itself has mostly erased. This is not a rush through facts. It is a chain of cause and effect. A fact becomes more powerful when it changes the way the next fact is heard. So the journey ends where it began, above Earth, looking down. The planet still appears calm. Clouds move. Oceans reflect sunlight. The Moon travels beside it. The night side glows faintly. But now the calm has depth. Earth is not calm because nothing happened. Earth is calm because so much happened, and because enough of those events settled into balance. The universe built home from shockwaves, dust, lightning, gravity, molten iron, impact debris, ice, orbit, and time. And for tonight, that is enough to hold. A blue planet beneath a quiet moon. A long, violent history softened into water, air, stone, and sleep.